Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to be going through section 10.4, the last section of chapter 10, dealing with areas and lengths in polar coordinates. Now remember that back in 10.2, we talked about how to apply area and arc length to parametric equations. We're going to do the same exact thing for polar coordinates, and we're going to make those formulas for area and arc length. I will also present the formula for surface area, although it will not be used in this section, just so you can use it as a comparison piece. The most important thing to think about with polar equations is that unlike Cartesian equations, where we would make a cross-section that would look like a rectangle, for example, we would have a curve like this, and we would construct a cross-section like so, and we'd try to find the area of each cross-section. That's not going to work with polar coordinates because we don't care about an x and a y axis. With polar coordinates, we have the single axis, and when we have some curve, which is usually going around this, something like this, then when we want to find this area, what we're going to do, or if I make this a weirder curve, something like this, when I find this area, what I'm going to do is instead make a sector. So an area of a sector like so. And I'm going to find the area of that sector, and then the area of another sector like here. And I'm going to try to keep adding those together, considering some difference of an angle measure. That's going to be the width of that area of a sector. The area of a sector from trigonometry, we have the formula for that as r squared, or the radius squared, times theta divided by 2, where theta is in radians. R is going to be the radius, or our function itself, because we typically have a function defined as r equals some function of theta. With all this in mind, since we're doing these areas of sectors instead of areas of rectangles, we have a little bit of a different area formula. We have that as you increase how many small pieces you have, or basically how many different area of sectors you have, what you approach is this integral equation from a to b, where a to b are angle measures. So this would be angle A, this would be angle B, of 1/2 r squared d theta. That coming from the formula for the area, r squared theta over 2. Now we'll commonly pull that 1/2 out because it is a constant, but this is going to be the formula. It's going to look a little bit different, and what a lot of people will relate it to is the volume formula based on circles or cells. So it's going to look a lot like volume equals pi r squared dx or dy. It's going to look a lot like that formula. Now that's going to be the formula for area. We can also do length. Now thankfully we can take just the formula for parametric equation of length, which is the square root of dx over dt squared plus dy over dt squared, and instead of dt, we just make those d thetas. This is useful in the case that we have x is equal to some amount of r and theta, and y is equal to some amount of r and theta. If we take the general equations of this, which is x equals r cosine and y equals r sine, these equations we established at the beginning of 10.3, we can rewrite the above equation by finding both the derivative of x with respect to theta of this equation and the derivative of y with respect to theta of this equation. This way we can hopefully result in something that just involves r and theta and no y or x, because we very seldom will have that in a polar equation. So what we need to do is take the derivative of each of these. The derivative of r cosine, that's a product rule. So it would be the derivative of the second, which is negative sine times r, so you get negative r sine theta, plus the derivative of the first, which is dr d theta times cosine. And you get the similar looking thing for the derivative of dy d theta. If you square these, you get this as a result. I already have this typed out here because this gets kind of lengthy. So r squared sine squared, then negative r sine times this, you get negative 2r dr d theta sine theta cosine theta, which looks ugly, but wait for a moment. And then you're also going to get the second thing squared, dr d theta squared and cosine squared theta. And you'll get something similar for the second piece. However, what we note is that we have a minus 2r dr d theta and a plus 2r dr d theta, both with sine theta and cosine theta, which means that these two pieces will cancel each other out, leaving just the dregs remaining. And actually, this has a little bit of a typo. These should be sine squared and cosine squared. What we note is that this is sine squared and cosine squared. That equals 1. And cosine squared plus sine squared, that also equals 1. So then all we have remaining is r squared plus dr d theta squared. That will allow us to replace dx d theta squared plus dy d theta squared with this. And so we get a new formula for the length, just substituting this new equation into that square root. And now we have something that's defined just using r and theta. And now we have bounds from a to b, where a and b are angle measures. So this is how you would find area, arc length, and if you want to do surface area, I have the formula down here as well. It would just be the length equation times 2 pi y if you're rotating around the x-axis, or 2 pi x if you're rotating around the y-axis. However, you will not use this in this chapter, or really in this class. But just food for thought and good for comparison pieces to the previous equations. So these are all the different types of ones we have: area, arc length, and surface area for all Cartesian, parametric, and polar. Okay, so that's a quick rundown of what the equations are and where they come from, or at least a couple of them. The next few examples we're going to do is we're going to do a couple examples of area with polar equations, and then we'll do a couple with length. Alright, so again, what we're going to do is find the area in the first quadrant here of r equals 3 minus 2 sine theta. So a couple things. First, I'm going to have the formula for area written out, because particularly if it's something that's new to us, we always want to write out the new formula. That is, a is from a to b of 1/2 r squared d theta. So this new equation. And the other thing I want to do is, usually I should want to graph this to get an idea of what this looks like. Particularly if you're new to polar equations, if you're still working with them, start graphing them a lot so you get familiar with them, until you get to the point that you can look at this and you know what it looks like. If I do graph this, plugging in values for theta, this one doesn't have anything multiplying theta, so we could just use the typical values. If I plug in 0, sine of 0 is 0, so you get 3. You get pi halves, you get sine of pi halves is 1, so 3 minus 2 is 1. Pi, you also get 0, so you get a value of 3 overall. 3 pi halves will give you negative 1, so that's 3 plus 2 is 5, and then you'll get back to 3. If I try to graph that, I see this goes up to 5, so I'll say 1, 2, 3, 4, maybe make this a little bit longer. 1, 2, 3, 4, 5. And I'll graph my points appropriately. I'm going to need to know where 1 is, so I'll make a concentric circle for that. I'm going to need to know where 3 is, so I'll make a concentric circle for that. It's usually how I draw polar if I don't have a graph already made. And then same thing for 5 all the way around. Then that'll let me draw my points. First, angle 0 is right here with a radius of 3. Then angle pi halves, we have a radius of 1. Angle of pi, we have a radius of 3. Angle of 3 pi halves, we have a radius of 5. And then we're back up to 3. What this will look like is something similar to this. We recognize this as a limacon, and if I look at my values, if I look at A and B, I notice that 3 over 2 is between 1 and 2, so this is a dimpled limacon. So it agrees with this. It's basically a limacon that looks a little bit flat, or has this little kind of dent in it. And that's what we see here. So this agrees with the information we knew from before. Now, if we're trying to find the area in the first quadrant, that means we don't want the area of this whole thing. We want just this region here. Now remember, this doesn't mean that with rectangular coordinates, for example, we would make a rectangle here, and then we'd find the area of all those. That's not what we do in this case. What we're doing when we find area with polar is we make a cross-section that looks like this, an area of a sector, and that is going from angle measure A to angle measure B. So here then we notice that the area in the first quadrant, this point was defined at theta equals 0, and this point was defined at theta equals pi halves. So then we can use this area formula then and say area is equal to, from 0 to pi halves, of 1/2 times our function 3 minus 2 sine theta quantity squared d theta. Alright, so that's the only piece that I'm looking for. Now, this will require some manipulation, or expansion anyway. This will give us, maybe move out a little bit. This will give us 0 to pi halves of 1/2 times, if I square all this, I'll get 3 squared is 9, 3 times -2 is -6, times 2 is -12 sine theta. And then -2 sine theta squared will give you plus 4 sine squared theta d theta. This we could take the integral all day, but sine of theta we need to replace, and what we can replace it with is the double angle identity, or the power identity, of 1 minus cosine of 2 theta divided by 2. That's what we can replace sine squared with. If I pull the 1/2 out, from 0 to pi halves, we have 9 minus 12 sine theta plus 4 times 1/2 is plus 2. Plus 4 times negative cosine 2 theta over 2 will give you minus 2 cosine 2 theta d theta. And we could just combine that 2 and 9 to make 11. That we can take an integral of now. And so we have 1/2 times 11 theta plus 12 of cosine of theta. And this is going to give us minus 2 divided by 2, or just 1 times sine of 2 theta. From 0 to pi halves. If we evaluate this, first with pi halves, we get 11 pi halves plus 12 times cosine of pi halves, which is 0, minus sine of 2 times pi halves, which is sine of pi, which is also 0, minus, we have the rest, 0, plus 12 of cosine of 0. Careful, cosine of 0 is actually 1, so that's plus 12. But sine of 0 is 0. So then overall we have 11 pi over, looks like 4, minus 12 divided by 2, so minus 6. So that'd be our final answer. Or if you find this as a decimal, you get 11 pi divided by 4 minus 6 gives you about 2.64. So that would be the area in this region. Okay. So overall, we just basically need to know what the bounds are. Sometimes they're not explicitly stated. And then find just the area of that applying the formula. We can still use our rules from trig substitution and from trig integrals to help solve these. Example 2 is going to be a little bit longer, which is why I give it a little bit more space. we have find the area of the region inside r equals 4 plus 4 cosine and outside r equals 6. This is going to be a little bit more complicated because we need to consider what this region looks like first. Now, r equals 4 plus 4 cosine of theta, that's going to be another limacon. And because 4 and 4 are equal to each other, we know that this is specifically a cardioid. If I were to try to graph this, you can do with points as well, but I'm going to do without. 1, 2, 3, 4, 5, 6, 7, 8 is as far as I'm going to need. If I plug in, say, 0 into this, I get 4 plus 4 is 8. If I plug in pi halves into cosine, I get 0, so I get 4 overall. So I'm going to need to know where 4 is. Might not give us enough room, actually. Something like that. Okay. And I'm also going to need to know where 6 is. This should be fine, though. Okay. So if I plug in, as I said, pi halves, we get an answer of 4, so that means it comes in over here. If we plug in pi, we get -1, so we get 0. 3 pi halves will give us 0 again, so we get 4 plus 0 is 4. And we're back to 8. We know this is a cardioid, so we know that when we connect these points, this curves in, makes a heart, and comes out back like that. So this I have in red. So this function is in red. If I do r equals 6, which is itself a function, maybe I'll do that one in blue. So this one in blue, that's just a circle with radius of 6. So I already kind of outlined that. That is this function here. So that means when they say the area of the region inside r equals 4 plus 4 cosine and outside r equals 6, that means what we're looking for, if I maybe do this in black, is this region right here. That'd be inside r equals 4 plus 4 cosine and outside r equals 6. So that means what we need to know is the angle measure here and the angle measure here that defines that. From the origin, once we find that region, we have cross sections, for example, that would look like this out to the edge. That'd be a cross section. And so if I want the area in this black region here, all I would need to do is find the cross section to this curve minus the cross section to this curve. So we're going to do a difference of functions, just like we would for normal rectangular coordinates, where we would have a function down to some other function. We would find the area up to this one, and then we'd subtract away the area down to the bottom one, and we'd get the area just in the middle. Likewise, I'm going to just cut out that cross section and hopefully just get this piece here, and maneuver that through the angle measures involved. So that means I need to solve for this, where they equal to each other, and thankfully this one shouldn't be too bad. If I solve for these, I have r equals 6 and r equals this, so we could set 6 equal to 4 plus 4 cosine theta. That means minus 4 is 2 equals 4 cosine theta. Divide by 4, I get 1/2 equals cosine of theta. And this may require trig knowledge, but cosine of theta equals 1/2 at a few places. It equals pi halves at pi, or 1/2 at pi thirds, and also at technically 4 pi thirds. Or if I want to keep a clean sweep here, I'm going to say negative pi thirds. Like when we draw this, we go counterclockwise, so I'm going to say this is my A, this is B. Note that I don't want to use pi thirds and 4 pi thirds, even though these are equivalent angle measures. This would be a different rotation. Pi thirds would be the lower one, and then it'd be finding the area this direction. So it'd actually be trying to basically find the area here, which is not what we want. Now, since we know what we're doing, we're again going to apply our formula. So area equals 1/2 of a to b r squared d theta. And specifically, we're going to do a subtraction of these. So our area is going to look like 1/2. It's going to be 1/2 on each of those. So 1/2 times from negative pi thirds to pi thirds of 4 plus 4 cosine theta squared d theta. Notice that that's the outside curve is 4 plus 4 cosine of theta. Kind of like with rectangular, I would take the furthest one from the axis. Likewise, I'm doing the furthest one from the origin. And I'm going to subtract away the area from the inner cross section, or the inner sector here, which is just 6 squared d theta. That 1/2 multiplying both of these. Some of this isn't too bad. We can solve some of this already. This would just give you 36 theta times 1/2, so it's going to give you 18 theta. So we're going to have 1/2 times this integral from negative pi thirds to pi thirds. And this squared will give you 16 plus 4 times 4 is 16 times 2 is 32 cosine theta plus 16 cosine squared theta. You can also pull the 4 out initially if you wanted to. D theta. And then we're going to have minus, we determined this was 36 times 1/2 is 18 theta. And that's going to be from negative pi halves, or pi thirds, to pi thirds. With a little bit of work, we can solve this. Again, we see that cosine squared, that's the only problem, but we can replace that with 1 plus cosine of 2 theta over 2. And so what that'll give us is 1/2 negative pi thirds to pi thirds. This will give us 16 times 1/2 is 8, plus this 16 will give us overall 24, plus 32 cosine theta, plus 16 times 1/2 of cosine, so that's plus 8 cosine 2 theta, minus 18 theta. So overall we get, this will be 24 theta times 1/2 is 12, minus this 18 theta will give us a negative 6 theta. But for the rest of that, we're going to have 32 cosine. That's going to turn into 32 sine times 1/2 is 16 sine theta. 8 cosine of 2 theta. That's going to turn into 8 sine of 2 theta divided by 2. And then times another 1/2. So divide by 4. So it'll give us plus 2 cosine of, or sine of 2 theta. And then minus that 6 theta from negative pi thirds to pi thirds. Don't think I missed anything there. 24 times 1/2 is 12. Minus 18 is all good. 16 sine theta, yep. And this one turns into sine of 2 theta divided by 2 times 1/2. We get that. Okay, all good. And then we can evaluate this. All right, so plugging those values in. We get, we don't have the outside, so just plug in pi thirds. We get 16 of pi thirds. Sine of pi thirds is root 3 over 2, so that's 16 root 3 over 2, or I guess that would be 8 root 3. Pi thirds again into sine, but that's sine of 2 times pi thirds. That's 2 pi thirds, but that's going to be the exact same thing. That's still going to give you root 3 over 2 times 2 will just be plus root 3. We'll combine that in a bit. Minus 6 times pi over 3, which will give us 2 pi. Minus, if I do negative pi thirds, sine of negative pi thirds, that will give us negative root 3 over 2 times 16 will give us negative 8 root 3. Likewise, for sine of 2 times negative pi over 3, I'm going to get the same thing, just a minus root 3. And then into here, we get minus 6 theta times negative pi over 3 will give us positive 2 pi. Note that these do not cancel out. They actually combine together. So we have 8 root 3 plus root 3 is 9 root 3, and this will give us another 9 root 3, totaling to 18 root 3. And then we have minus 2 pi minus positive 2 pi, so that's overall minus 4 pi. And that's going to be our answer there. Note one last thing, particularly when you're doing areas like this, you do want to make sure that your area is positive, because area should be positive. If I look at this, this is 18 times something bigger than 1, so something bigger than 18. This is 4 times pi, which is roughly 3-ish, so this is close to 12. So something bigger than 18 minus 12, this is going to be positive. Don't even need to do a calculator to check that. So those are a couple examples of using area. Now for using arc length. Okay, now remember we have to use our arc length formula, which we developed as L equals from A to B of the square root of, instead of the 2 derivatives squared, we have r squared plus dr over d theta squared d theta. Okay. Now, solving for this one with r equals e theta, this one actually is going to be relatively easy. We have r equals e theta. That means the derivative of r with respect to theta is still e theta, which is really nice. And so we get the length then, here from 0 to pi, is the square root of e theta squared plus e theta squared d theta, or 0 to pi square root of 2 e to the 2 theta d theta. That simplifies to the square root of 2 we can pull out from 0 to pi of e to the theta d theta. So we get just simply root 2 e to the theta from 0 to pi. So that gives us root 2 times e to the pi minus e to the 0 is 1. And that's our full arc length. Not too shabby, but again, most won't be as easy as just plugging e to the theta. A lot will involve some trig functions, so let's do a more complicated function like that then. Something like the arc length of the full cardioid of 1 plus cosine theta. Now this is a cardioid because A and B are equal to each other. This one should look like, if I just draw a rough sketch of it, this one should look like this. From 2 to 0. 2 I know because if I plug in 0 I get 1 plus 1 is 2. So I know how far that goes. But that's what we're doing. What we're trying to find is this full arc length all the way around. So let's start to do that then. Again, we have our standard formula, L equals from A to B, square root of r squared plus dr over d theta squared d theta. Always in good practice to write down a new equation when you just learned it, even if it's familiar to other ones. And to solve this, we need both r and dr d theta. Well, r is equal to 1 plus cosine theta. That's easy enough. Dr d theta also shouldn't be too bad. That's going to give us 1 derivative is 0 plus cosine theta derivative. That will give us negative sine theta. The negative is about to be irrelevant because when I plug these in, and notice this arc length goes from 0 all the way around to 2 pi, we have the square root of r, 1 plus cosine theta squared, plus negative sine theta squared d theta, which is why the negative is going to be irrelevant, because we're going to square it. This gives us 0 to 2 pi square root. The first one squared will give us 1 plus 2 cosine of theta plus cosine squared theta. And the second one will just give us a plus sine squared theta. We notice these last two pieces cosine squared plus sine squared equals 1. So this overall is 0 to 2 pi of 1 plus 1 is 2 plus 2 cosine theta d theta. Or if I pull out that 2, root 2 times 0 to 2 pi of 1 plus cosine theta d theta. Now you may be thinking, oh wait, does this mean that we're stuck here? Thankfully, no. Because this should look like something similar. Not the entire thing, but this should look a lot like what we know for cosine squared theta being 1 plus cosine of 2 theta over 2, the double angle identity, or the half angle identity, rather. Well, all I have here is instead of 2 theta, I just have a theta. So if this is double, then that means this should be theta over 2. And if I multiply the 2 over, I get 2 cosine squared theta equals 1 plus cosine theta. So I can replace this inner value using that identity. And don't forget the pi halves here. When we plug in this simplification, we have root 2, 0 to 2 pi, of, this is going to turn into 2 cosine squared of theta over 2 d theta. That root 2 we can pull out and combine with the other root 2 to give us total of 2 from 0 to 2 pi. Of cosine squared to the root is just going to be cosine of theta over 2 d theta. That, if I solve, will give me multiplication of 2 on the outside. So we're going to get 4 sine of theta over 2 from 0 to 2 pi. Again, that multiplication of 2, you could do a u substitution here if you want to, saying u is theta over 2, du is d theta over 2. So you would have to multiply this by 2. That's where that extra 2 is coming from. Now, this seems all well and good, but there is going to be a problem when we try to plug these values in. If I try to plug in 2 pi, we get sine of 2 pi over 2 is sine of pi, which is 0, minus sine of 0 over 2, sine of 0 is also 0. So we get an answer of 0. However, again, we know that this is a cardioid. We know that this looks like that. The arc length is not 0. What happened here was the fact that when we went from these arc lengths here, 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 we're just cross-sectioning here. At this point, once I get here, the values for y start to become negative, or the values for the radius start to become negative overall, or theta really start to become negative. So we need to be more careful with this. Instead of going from 0 to 2 pi, what we can more simply do is just find the length from 0 to pi, and because we know that the cardioid is symmetric, we could just double this. So instead, we can double the length of 4 sine of theta over 2 from 0 to just pi instead. Or if you wanted to, you could also split this up into 4 sine theta over 2 from 0 to pi, and then add 4 sine of theta over 2 from pi to 2 pi. The problem is that the positive and negatives are canceling each other out, so we needed to consider where it changes sign. And sine changes its sign from pi to 2 pi. But if we do this, this is going to be a little bit easier. We just get 8 sine of theta over 2 from 0 to pi. That'll give us 8. Sine of pi over 2 will give you 1. Minus sine of 0 over 2 will give you 0. We get an answer of 8. The arc length of that cardioid is 8. 8 units. Nice and simple. Again, if you did it the other way instead of splitting it, you would get 4 sine of theta over 2 from 0 to pi, plus 4 sine of theta over 2 from pi to 2 pi. If you do this, you'll get 4 times sine of pi over 2 is 1 minus 0 again, plus 4 of sine of theta over 2. If you do 2 pi, you get sine of pi is 0, minus if you put in pi, you get 1. Or actually, you get 1. So what we notice here is that the length from 0 to pi is a distance of 4, and the length from pi to 2 pi is a distance of negative 4, because it'd be 4 times negative 1. So that is why we were getting an answer of 0 earlier. But if we just double that, we get rid of that answer of 0, or if we consider that a negative length doesn't make sense, we should know that 4 plus 4 should give you 8. Either way, I think this way is a little bit easier, but to each their own. With that said, that's everything for this section. Hopefully a little bit shorter and easier than before, because we're just doing integrals, basically. If you have any questions, feel free to put those in the comments below, or ask your instructor directly. I hope you have a nice day.